So, this week we will talk about the multi-rate signal processing. So, what the title of the talk of this week will be the multi-rate signal processing. So, what do you mean by multi-rate signal processing? What is the meaning of multi-rate, the word multi-rate? So, what is signal processing? When I say the multi-rate, what do you mean by signal processing rate? Rate of signal, what do you mean that? So, let us talk about the digital signal processing. So, digital signal processing, when I say, then I say let us say XAT is a time domain signal. XAT is a time domain signal. When I say that the XAT is sampled with a sampling frequency Fs, then I know that I get the digital signal x of n after quantization. Now, then what is the rate? The rate means the rate at which I collecting the sample. So, if I say that my whole signal is in a single rate, that means the XAT is sampled in Fs, then I call it is single rate DSP, single rate signal processing. What is the meaning? Meaning is that let us I have a system, I have an input x of n, I have a system let us say h of n, then I have got a y of n. Now, if I say the sampling frequency of x n, sampling frequency for h n, sampling frequency of y n all are same as Fs, then I call it is a single rate signal processing. So, I have not changed the rate of the signal, that means sampling frequency of the signal. So, x n is sampled as Fs, h n or the processing is also done on sampling frequency Fs and output is also in Fs. Then I said it is a single rate signal processing. So, single rate means all the data is sampled the same rate, no change of rate within the system. So, when I apply x n in the system, I do something, I get y n. So, in this process, I never change the rate of the sample. So, sampling frequency will remain same. So, that is called single rate DSP system. Now, once I call the multi-rate DSP system, in this case signal processing which will use more than one sampling rate. So, in that case, in multi-rate, it is not that x n may be in Fs, y n may be I want Fy. So, the sampling frequency of y n is different from sampling frequency x n, or I can process in different sampling frequency Fy and then I get the output. So, when I say that in a DSP system, when I use multiple sampling frequency inside the system, then I call it is multi-rate signal processing. So, single rate signal processing throughout the DSP system my sampling frequency is Fs. Multi-rate signal processing throughout the DSP system there will be different kind of sampling frequency I will use. That is why it is called multi-rate signal processing. Now, what is sampling? As we studied in the week number 1 that I have an analog signal XAT, then I have converted to x of n capital T, where capital T is equal to 1 by Fs. That means a continuous time is discretized, or discrete signal I am making, discretized. So, continuous time is discretized using an interval t. So, after every t interval where t is equal to 1 by Fs, I am collecting the sample. So, if I say my Fs sampling frequency is 8 kilohertz, then I know within 1 second I will get 8k sample. So, 1 second I will get 8k sample. Now, once I say that Fs is equal to 16 kilohertz, then within 1 second I will get 16k sample. So, if you see, if I increase the sampling frequency, number of sample is increasing. number of sample within unit time is increasing. If I say I have a signal which sampled is equal to 8 kilohertz and I collected for 20 millisecond signal, then within 20 millisecond there will be a 160 sample. But when I said same signal, if I sampled at 16 kilohertz and I am collecting 20 millisecond signal, then I know within 20 millisecond there will be a 320 sample. So, when I increasing the sampling rate, the number of sample per second is increasing, number of second within a time is increasing. So, that means if the Fs is high, then number of samples also increasing. Then if I say okay, I know the sampling frequency, I know. So, what is sampling frequency is nothing but the x of nt, t is equal to 1 by Fs. So, in 1 second for 8 kilohertz sampling frequency, I get 8k sample, 8 kilo sample. Now, if I want to know what is the inside the frequency domain, let us say I have a signal xat and which sampling frequency is Fs is equal to 8 kilohertz and I get x of n. Then as per the Nyquist rate, that what is the maximum frequency contained in the xn? What is the maximum baseband frequency? So, I know the maximum baseband frequency is 4 kilohertz. So, if the sampling frequency is 8 kilohertz, then I can say that the maximum frequency contained in xn is equal to 4 kilohertz, which is nothing but a Fs by 2. Now, when I converting xat to x of n, that is why the analog to digital conversion ADC, analog to digital conversion, what I use? I use anti-aliasing filter. So, here is a xat, there is a filter which restricted, or I can say the band limited the input signal with 4 kilohertz. Then I convert to ADC and I get x of n. So, there is an anti-aliasing filter which band limited the signal xat with 4 kilohertz if the sampling frequency is 8 kilohertz. So, I can say when I say a digital signal, that is automatically it is a band limited signal. Whatever the signal is highest frequency will be Fs by 2, that is the limited by anti-aliasing filter. So, if I say that I have a signal which has a 4 kilohertz frequency. So, up to 4 kilohertz I have a signal, or if I say this axis is omega. So, what is omega? Omega is radian per sample. So, omega equal to 2 pi f by f, the analog frequency content divided by Fs. If I say that I have a signal whose maximum frequency is 4 kilohertz and sampling frequency is 8 kilohertz, 2 pi into 4 kilohertz divided by 8 kilohertz. So, I can say this is nothing but a 2, so it is nothing but a pi. So, maximum rate of oscillation exists in the baseband signal is pi to minus pi. That is my band limited signal. So, if I sampled it Fs, then what is the frequency domain representation? This axis is omega, this is 0. So, this is pi, this is minus pi. Then I can say here I have a Fs, Fs is nothing but a 2 pi. So, there will be an pi and there will be an minus pi. So, it is 2 pi plus pi and 2 pi, this point is 2 pi minus pi, which is nothing but a pi. Now, suppose I have a signal, let us say I have a signal xat whose highest frequency content is 2 kilohertz and I sample this signal with 8 kilohertz. Then if I want to draw the baseband signal So, this axis is omega, this is my 0, then I know what is the value of this point. This point is omega is equal to 2 pi 2 kilohertz by 8 kilohertz. So, 1 by 4 2 pi by 2. So, this is pi by 2, this is minus pi by 2. So, if I want to again draw this signal against the sampling after sampling frequency, I at the 0 I will get pi by 2, this is also pi by 2 minus pi by 2, let this is 2 pi, this point is 2 pi, this point is pi. So, I can get here also pi by 2 minus pi by 2. So, I know this is not aliasing. So, this is okay and this is the maximum frequency content. So, that is the frequency domain representation of the sampling. So, when I sample a signal, I get this kind of representation in the frequency domain. 2 pi is nothing but a fs. Then I will get another component here which may be 4 pi twice fs, like that way I will get it. So, fs is the sampling frequency. Now, I said I want to use a DSP system where instead of single fs I have a multiple sampling rate, that is why it is called multi-rate DSP system. So, let us say I have a system like this input is xn is in 8 kilohertz, I want to process it in let us say 4 kilohertz, and then I want to get the output in 6 kilohertz, yn is in 6 kilohertz. So, if you see the sampling rate for xn is 8 kilohertz, sampling rate for processing is 4 kilohertz, sampling rate for output is 6 kilohertz. So, different sampling rate I have defined, and that is why the whole system is called multi-rate DSP system or multi-rate signal processing. Now, if I say suppose I have a signal at 8 kilohertz. So, what I can do? I can either up the sampling rate. So, instead of 8 kilohertz I may say 12 kilohertz I can want, or I can down the sampling rate, or 8 kilohertz I want 6 kilohertz let us say. So, either I can increase the fs or I can decrease the fs. If I increase the fs, this is called upsampling. When I increase the sampling frequency, this is called upsampling. When I decrease the sampling frequency, this is called downsampling. So, to make it multi-rate signal processing, I may require to increase the sampling frequency or I may require to decrease the sampling frequency. When I increase the sampling frequency, this is called upsampling. When I want to decrease the sampling frequency, this is called downsampling. Practical life example. What will happen if I make it upsampling without restricting that? Suppose I have recorded a signal with 16 kilohertz, let us say you recorded an audio in 16 kilohertz. If I play it 22 kilohertz, then what will happen? Or earlier example, suppose if you see in a gramophone record that every record contained a fixed RPM, in top of the record it is written 60 RPM or 45 RPM or 80 RPM, all RPM is written. So, in gramophone record using a pin I am collecting the audio information 60 RPM, that means the rotation speed of the gramophone records is 60 RPM. So, if I have a gramophone record of 60 RPM, if I play with 80 RPM, that means I am upsampling the recorded signal. When I upsampling it, the quality of the signal will be changed because I am not converting it. In your tape recorder also, what is their motor speed? In tape recorder, if you see that record, the tape is rotating using a motor inside the tape recorder. If you increase the motor speed, what will happen? a female voice, a male voice is become female voice. If you decrease the speed, female voice become male voice. You can see it. So, lot of things will happen. So, I can say that if I recorded a signal in 8 kilohertz audio signal, I have to play with 8 kilohertz, then I get the original sound. If I recorded a signal in 8 kilohertz, if I play it 16 kilohertz, then I require, I am only playing, I am not processing it. So, when I say upsampling, I am not only playing it, I am processing it. So, what I want in case of upsampling also, I do not want the signal quality should change. So, in case of upsampling process, I have an 8 kilohertz sampling frequency, I want to make it 16 kilohertz, I do not want the change of the signal, quality of change of the signal. So, it is not the example of like the tape recorder. If I change, so in tape recorder I am basically not upsampling, I am not completing the process, I am playing it only very high sampling rate. So, there is a change of frequency is happening. So, upsampling also there is a concern. So, if once I say the upsampling, so can I upsample it without knowing that what is happening in the signal? That means what I am saying that suppose I have a signal of 8 kilohertz. So, when I say I want to change the sampling frequency, let us say I have a signal with 8 kilohertz, I want to change the signal to 16 kilohertz. So, I have an x of n recorded with 8 kilohertz. So, in 20 millisecond I have 160 sample. But if I want to change the fs is equal to 16 kilohertz, then in 20 millisecond I have 320 sample. That means number of sample is increased by 2 times. So, suppose I have an xn which is nothing but let us say 1, 2, 3, 4, 1, 2, 3, 4 all are the sample value. So, this is x0, this is x1, this is x2. Now, if I say, when I say let us say this kind of 160 sample is there. Now, I want to make it 320 sample within the same time. So, how can I do that? So, I can say that in between 2 sample I can put 1 sample, 1 0. So, I can say x0 is equal to 1, but x1 is equal to 0, x2 is equal to 2, x3 is equal to 0. So, what I am doing, since I have to increase the 2 times, so let us the I is equal to 2. So, upsampling factor I called I is equal to 2. So, upsampling factor is 2 because I have 160 sample, I want to make it 320. So, in sampling frequency I have an fs equal to 8 kilohertz, I want to make it fs is equal to 16 kilohertz. That means, I is equal to 16 by 8 is equal to 2. So, how do I do that? I can put like this way. So, instead of 160 sample, I get 320 sample. So, I putting a 0 in between a sample. How many 0 I have to put? I minus 1. If I want to make it fs is equal to 24 kilohertz, then number of sample will be how much? 160 into 3, 3 times. I am upsampling 3 times. So, that means 480 sample. So, if I want to make it 480 sample, that between x0 is equal to 1, then x1 will be 0 and x2 also will be 0 and then x3 will be equal to 2. So, I am putting in between 2 sample I minus 1 number of 0. So, in case of here it is 24 by 8 is equal to 3, I equal to 3. So, I am putting I 3 minus 1 2 number of 0 in between 2 sample. So when I am making upsampling, I am putting 0, which is called interpolation. Upsampling sometimes is called interpolation. So I am interpolating the signal in between. So what is the new t? So in case of 1 and 2, the distance between the two sample, time distance is t. T is equal to 1 by Fs. Now once I say it is upsample, that means Fs is equal to 8 kilohertz. Now once it is Fs is equal to 2 times, that means t is reduced by 2 times. So that's why I have to put another sample in here. So this is called upsampling. So now I put an 0 here. So what will happen in frequency domain? I have to think on that also. Unless what will happen? If I put it, the sampling frequency is changed. But if I when I give the example of tape recorder, I am not inserting 0. What I am doing, I have recorded the sample, 160 sample I have recorded. So within 20 milliseconds I supposed to play 160 sample, but since I speed is double, I am playing it within 10 milliseconds. So that means 20 millisecond signal is squeezed to 10 millisecond signal. So the frequency domain it will be changed. But what I want, I do not want that frequency domain it should be changed. Next one is, suppose I have an 8 kilohertz signal, I want to downsample it. That means I want to decrease the sampling rate, let us say to 4 kilohertz. So up by 2, down by 2 also. So I can either downsample it or I can upsample it. So downsample means I have to, so instead of 160 sample in 20 millisecond, there will be only 80 sample. So what is? Out of 160 sample, I have to pick up every alternative sample. So I get the 180 sample. So that is called downsampling. Now downsampling, upsampling we understand. Then why I do that? Why I do downsampling and why I do upsampling? So useful for dissemination or downsampling. Why called dissemination? I am saying when I say out of 160 sample I want to make it 80 sample, that means some of the sample I am discarding. So that's why it is called dissemination. So downsampling is called dissemination. So 160 sample to 80 sample. So it is reduce the number of sample. So if it is reduced, then reduce the data processing. Suppose I want to implement a convolution and I have a signal which is 80 kilohertz is the sampling frequency, and I taken window size is equal to 20 millisecond. So when I say that, I said 160 sample is there. So I know convolution equal to n equal to 0 to n minus 1. Capital N is equal to 160. X of n into, let us say, h of n, let us say it is n minus k. So this is k, this is not 1. So k equal, n equal to 160 sample is there. So when I say the convolution, if my data size is increases, the complexity is increases. If the data size, so instead of 8 kilohertz, if I say the sampling frequency is 4 kilohertz, then I know within 20 milliseconds I have only 80 samples. So my processing time will be decreasing. So it is reduced data processing, create low computational count or narrowband filter, and also power dissipation. So you know that any handheld device, when I say the power dissipation factor, the P is equal to CV square into F. F is the frequency. So if my processing speed is slow, then the power dissipation will be less. So when I process the data inside the DSP processor, if I say I want to process it low sampling frequency, that means rate of data is low. And also it requires less memory. Suppose I said I have a sampling frequency 8 kilohertz. If I want to 2-second data, I require, and each sample is 2 bytes, then I know I require 8 into 2 into 2 kilobyte space, which is equal to 32 kilobyte. Now let us say same signal I sampled at 4 kilohertz, 2-second data, 2 bytes each sample. So 4 into 2 into 2, I required 16 kilobyte. So now storage space is reduced. So when I downsample the signal, the storage space also reduced. Similarly, in case of upsampling or interpolation, useful for effectively increase the resolution of the DA, digital to analog converter. So suppose you know that suppose I have an 8 kilohertz sampling frequency. When I want to convert to analog signal, what I want? I want exact copy of that input signal. So, if the number of sample within a time is increases, the efficiency or effective, I can say the increase the resolution of digital to analog converter. So suppose I have a signal x of n in 8 kilohertz, I process it within 8 kilohertz, and then output I increase to 16 kilohertz, upsampled it, and then apply digital to analog converter. Then what will happen? Effectively, my sampling frequency is increasing. That's why the resolution of my digital to analog converter will be increasing. Useful for pulse shaping filter. I will come to that point. Useful for combine several independent narrowband channel into one wideband data stream. Suppose what I want, let's say I have a signal. So you know, if I have an Fs, the Fs is equal to 8 kilohertz. So you know that the distance between 0 to this is to Fs. Fs is 8 kilohertz. So what is the bandwidth? Bandwidth is basically the signal I can keep within that Fs is Fs by 2. So 4 kilohertz. Now once I increase the Fs, that means Fs is equal to 16 kilohertz. Then the effective bandwidth of the baseband signal is Fs by 2, 8 kilohertz. So instead of 4 kilohertz, I can put 8 kilohertz. So I can put lot of narrowband channel into a single Fs. And also sometimes simplify computation. If I increase the sampling frequency, sometimes not the computational complexity, computation. So like in case of filtering, let us say if the transition bandwidth is increases, then the order of the filter is decreases. So somehow if I upsampling process help me to increase the transition bandwidth, then I can say the order of the filter is decreases. I will give you an example for this. Let us say another first example, that if you go to any recording studio, you can see the recording studio use 192 kilohertz sampling frequency for master voice. That means when the recording studio record that audio signal for master cassette, they use 192 kilohertz sampling frequency. But any audio CD, the sampling frequency is 44.1 kilohertz. So I have an Fs which is 192 kilohertz. Now I want to Fs which is equal to 44.1 kilohertz. So I have to downsample it. So Fs is there. I require an Fy. So I have to downsample it. So Fs is equal to 192 and Fy I required 44.1. So how much downsampling factor I required? I can easily calculate Fy by Fs. Fy by Fs is nothing but a 44.1 divided by 192. So that is my fraction of, but downsampling, when I say that can I select, so when I say let us say there is a 4 sample, I want to reduce the downsample by 2. So, that is 2 sample, that means I select this sample and this sample, I discard this sample in this sample. But I cannot say 1.5 sample, how can I discard? But this can be easily implemented using upsampling and downsampling. I am coming details in later. For speech analysis, we use 16 kilohertz sampling frequency. So, 192 has to be reduced to 16 kilohertz. For speech coding, 16 kilohertz. Telephone bandwidth, 8 kilohertz. So, from master voice, can I downsample it like that way? Or can I upsample it, downsampling? So, lot of application I required where I required a downsampling, where I required an upsampling. So, how do I do that? Next example, where I said that sometime upsampling that decrease the complexity of the system. For example, let us say I have an audio bandwidth. You know the audio bandwidth is 20 kilohertz is the maximum bandwidth of the audio signal. Perception of the human being can perceive audio up to 20 kilohertz. Okay. So, if it is 20 kilohertz, then I know audio CD sampling frequency is 44.1 kilohertz. Okay. Now, what is Fs by 2? 44.1 divided by 2, that means roughly 22 kilohertz. So, maximum signal can contain if the sampling frequency is 44.1 kilohertz is equal to 22 kilohertz. I know my audio bandwidth is 20 kilohertz. So, think about when I design the analog to digital converter, my first step is anti-aliasing filter. So, what is the property of this low pass filter, low pass anti-aliasing filter? I required up to 20 kilohertz flat response. Then I know that within 22 kilohertz it must be sufficiently attenuated, so that aliasing can be avoided. So, I can say within the transition bandwidth 22 minus 20. So, this is omega p, the Fp, and this is Fc. So, I can say Fc minus Fp 20, that means within 2 kilohertz this has to be sufficiently attenuated, let us say 96 dB attenuated. So, it is minus 96 dB. So, the transition bandwidth of the filter is 2 kilohertz. Now, you know the transition bandwidth and order of the filters are inversely proportional. If I increase order of the filter, then the transition bandwidth is decreases. So, if the low transition bandwidth is low, then the order of the filter will be very high. Okay or not? So, order of the filter will be very high. So, within 2 kilohertz, if I have to design the FIR filter, I know I require a high, the M will be very high. But let us say instead of design this, let us say instead of now my sampling rate is Fs is instead of 40 kilohertz, I said 44.1 kilohertz, I said it is 44.1 into 64 kilohertz. So, I 64 times I upsample the signal. So, 64 times I upsample the signal. That means, once I 64 time upsampling, then what is the Fs by 2 value? This divided by 2, which is nothing but a 44.1 into 32 kilohertz. So, if I say 44.1 into 32 minus 20 kilohertz, so there is a huge long transition bandwidth. So, if the transition bandwidth is very long, then I know the order of the filter is very less. But the problem is, I have to sample the signal is 44.1 into 64 into 2 kilohertz. Somehow I have to sample that signal. So, that required also another end. So, if I upsample it, but that is already done and by an anti-aliasing filter. So, it can be done, this is the notional. So, when I design and filter, sometimes upsampling can reduce the complexity of the filter. Now, I come to that overall system. So, when I say I have an X2, I have anti-aliasing filter and digital low pass filter and downsample, and then I get Xn. Because I have an Xn, I upsampled it, but again I have to revert back to the system. So, suppose I said, let us say, so XT ADC is 44.1 into 64 kilohertz. I have upsampled it, but I have to downsample it because I want Xn should be in 44.1 kilohertz. So, I have to downsample it. Okay. So, overall system diagram will be look like this. Now, suppose I have given you a problem. Suppose I have a signal with 8 kilohertz. I want to upsample it. Let us say I have a signal Xn is sampled at 8 kilohertz. I want to upsample it 20 kilohertz, 12 kilohertz. I want a signal Yn from Xn, which is Fs is Fy is equal to 12 kilohertz. Have you understand or not what I am saying? I have a signal, I have a signal whose Fs is equal to 8 kilohertz, x of n. I want another signal using a signal processing block, so that my output of the system is Yn and whose sampling frequency Fy is equal to 12 kilohertz. So, that is called sampling rate converter. So, when I say the sampling rate converter, so sampling rate converter nothing but a Xn is the input whose sampling frequency is Fx. I want an Yn as an output whose sampling frequency is Fy. So, the process of the system or inside that what I have to do, that whole system is called sampling rate conversion, or the system is called sampling rate converter. So, any system I have an impulse response. So, input index is n and output index is m, and that is why the sampling rate converter impulse response is represented by h n m, because index is different. If I say Fx is equal to 8 kilohertz, then in 1 second of Xn I get 8k sample. Then let us say Fy is equal to 12 kilohertz, then I know in 1 second I get 12k sample. So, index m and n is different. So, how do I do that? So, what I want Fy, what I given Fx. So, what is the ratio? Ratio is nothing but a 12 divided by 8. So, I can say 3, 4. So, 3 by 4, which is called I by D. I is the upsampling factor, D is called downsampling factor, or sometimes called interpolation factor, and D is called dissemination factor. So, what I will do? I will get an Xn. First, I upsample the Xn by 3 times. So, 8 kilohertz is upsampled by 3 times. So, it becomes 24 kilohertz. Now, it is 2. It is downsampled by 2 times. So, it is 12 kilohertz. So, I can say if it is upsampling, let us say upsampling, let us say this is an upsampler of I equal to 3, then I can say Fy is equal to 3 into Fx. If it is a downsampler of 2, I can say Fy is equal to D Fx by D. Let us say I give you another example. Suppose I said I have a signal x of n whose sampling frequency is, let us say, 16 kilohertz. I want to make x of n is equal to let us say 12 kilohertz or 10 kilohertz. What is the upsampling factor and what is the downsampling factor? So, input is fx is nothing but a 16 kilohertz and fy is equal to 10 kilohertz. So, it is nothing but a 10 by 16. So, I can say it is 5, it is 8. So, it is 5 by 8. So, I can say this fy by fx is equal to I by d, which is relatively prime. So, this is prime. So, 5, 8. So, I have to upsample by 5 times and downsample by 8 times. Okay. So, if I give you a problem, so let us say I have a signal frequency is 4 kilohertz, but at the output I want it should be 44 kilohertz. So, what should be the upsampling factor and what should be the downsampling factor? You can easily calculate. Okay. So, I will stop here and the next class I will talk about what is upsampling and what is downsampling. Okay. Thank you.